Welcome back, physicists, and today we're going to talk about our first worksheet in Unit 3, Balanced Forces. This is worksheet 1A. We'll have 1B next week. These are very similar, which is why they get numbered 1A and 1B. So the directions say in each situation represents the objects with a particle. Okay, cat becomes particle. We want to sketch all the forces acting on the object and making sure the length is representative of the magnitude or size. So forces that are a lot bigger should have longer lines. It also tells us to use congruency marks to indicate which vectors are equal in magnitude. So if the object is not in motion, we know the forces are balanced, or if the object is in constant motion, if it's not accelerating, we know they're balanced, so they would have to be equal to balance out. So let's look at this cat. Cat is motionless on a rug. All objects have gravity acting on them. We'll call that the force of gravity, Earth on cat. And the cat is not falling through the floor, so it must be supported by the normal force of the rug on cat. Since those forces are balanced, we know this because the cat is not falling through the floor, it's not accelerating up or down, it's just motionless, lazy cat. They are equal. There are no side-to-side forces acting on this. If I tried to push him, friction would start to act, and he might scratch me or whatever, but right now there are no side-to-side forces on that guy. Awesome. Let's look at the second problem with the ice skater. Switch to green. Okay, so ice skater is my system. I missed that part on the cat. Just the cat, not the rug, is in my system. The ice skater is in the system. Reduce the ice skater to a particle. Sorry, ice skater. And look at the forces. Gravity, the first force. Easiest one to draw, it's always straight down. Earth on skater. The person is not falling through the ice, so there must be a normal force to support them of the ice on the skater. And this says that the ice is frictionless. So even though the person is moving, there are no side-to-side forces. There's no friction. So they must have pushed off, and now they're no longer pushing, they're just coasting. So F net equals 0. It's at equilibrium. So there is motion, but it is not changing. So forces are balanced, and there's no unbalanced forces. Awesome. Great, let's look at 3. So softball player. I'm going to draw a line around my softball player. They are my system. I don't care about the plate or the ground. Reduce the softball player to a dot. They are a particle. And then let's look at forces. So she's slowing. So her velocity is this way, but she's slowing, so there's acceleration, which means F net is not 0. They're not at equilibrium. So let's think about what forces we do have. Always gravity. I'll call that the player, Earth on player. And normal, ground on player. And then how is she accelerating backwards? There must be a force that way, and because she's like sliding, that's going to be the force of friction because there's surfaces, and we'll call that ground on player, force of friction, ground on player. So we can make our equal marks. Normal and gravity are equal because she's not accelerating up or down, but she is accelerating backwards. Her velocity is forwards, her acceleration is backwards, so she's slowing down. Awesome. Okay, I'm not going to go through all of the rest of them. I'm just going to give you guys a quick explanation for some of them. So chandelier, make your chandelier the system, maybe even just this part of it. So there's a chain coming out of it in gravity. For this one, focus on just the bucket of water. Think about what the bucket of water is connected to. Doesn't matter that the person's over here at an angle if you make your system just the bucket of water. For 6, the skydiver is still speeding up. So think about what forces there are, and if they are equal, if they are speeding up, think about what direction the acceleration is going to be. Going off of that 7, now they are at a constant velocity, so they're not speeding up. The acceleration is 0, so F net is 0. There's no acceleration, so there's no net force. The forces must be balanced. Even though it's moving at constant rate. Okay, force of a ball rising. Think about what's touching it, what's acting on it. This one and 9 are connected, and hopefully you'll get it. If not, if you're really confused, come talk to me about it. For 10, the cork is floating in water. It's probably just floating there at rest, and we call the floating force the buoyant force, which you can abbreviate with a B. For 11, the airplane is straight and level, flying at a constant rate, so acceleration is 0. We call the force that makes planes fly, we call that force lift. We call that, we'll abbreviate with that one L. Great. And then the last one, 12. Magnetic force. You want your force or your object to just be the nail. Your system is just the nail. And we can call the force magnetic. It can be a force applied, or it can be a force magnetic, or you can abbreviate it M. Any of those are fine for a magnetic force. I think that's everything that I wanted to share with you about those. Great.